On March 9, 2011, a magnitude 7.3 earthquake struck Japan's Sanriku coast. 51 hours later, a magnitude 9.1 killed 18,000 people and melted down Fukushima. Yesterday at 7:52 UTC, an earthquake of nearly the same magnitude hit the same coast at the same depth, 180 kilometers north of 2011. That 51-hour window runs out later today. By the end of this video, you will understand what Japan is watching for and why it could change everything. Stay with me on this one, because the worst might be yet to come. Let's get into it. At 7:52 UTC yesterday morning, shortly before 5 in the evening local time in Japan, on April 20th, a major earthquake struck off the east coast of Honshu, along the Sanriku coast. The United States Geological Survey measured it at magnitude 7.4. The Japan Meteorological Agency later upgraded that number to 7.5 based on additional seismograph data. Both agencies agree on what matters. This was a major subduction zone earthquake. It happened at shallow depth, and it happened directly over the Japan Trench. The epicenter was located at 40.027 degrees north latitude and 142.968 degrees east longitude. That places it roughly 100 kilometers, about 60 miles, east-northeast of the city of Miyako in Iwate Prefecture. The depth came in at 10.9 kilometers, which in subduction zone terms is shallow. Shallow matters. Shallow is what generates tsunamis. Shallow is what gets felt across entire prefectures. Shallow is what moves the seafloor. The USGS pager alert was set to green. That rating indicates limited expected casualties and limited expected structural damage. It is important to understand what that rating means and what it does not mean. It reflects the fact that the epicenter was offshore, that the shaking at populated coastlines was reduced by distance, and that Japan's building stock is the most earthquake-resistant in the world. It does not mean this earthquake was harmless. The tsunami threat was immediate, and the question that opened the moment this quake was logged is the question this whole video is going to answer. As of the recording of this briefing, and more than 24 hours after the rupture, that question is still open. The Japan Meteorological Agency issued a tsunami warning within minutes of the rupture. That warning covered the Sanriku coast and the southern Hokkaido coast, a stretch of shoreline that extends for hundreds of kilometers along the Pacific side of northern Japan. JMA called for waves up to 3 meters. That is roughly 10 feet. It is the second highest tier in Japan's 3-level tsunami alert system. The top tier, major tsunami warning, is reserved for waves over 3 meters. This event came in just below that threshold. Evacuation orders went out immediately. Coastal residents were instructed to move to higher ground without delay, and the first confirmed waves arrived within minutes of the earthquake. Early measurements reported wave heights around 40 centimeters at the initial observation point. Japanese officials emphasized a point that anyone who lived through the 2011 disaster knows by heart. The first wave is rarely the largest. Tsunamis are wave trains. The dangerous water often arrives 20, 30, 60 minutes after the first pulse, and it arrives as a surge that does not recede. The NOAA tsunami warning feed independently confirmed an active warning centered at approximately 39.9 degrees north, 143.3 degrees east. The U.S. National Tsunami Warning Center confirmed no tsunami threat existed for the west coasts of the United States, Canada, or Alaska. This event's tsunami damage is local, and local on this specific stretch of coast has historically meant catastrophic. 5 nuclear power plants along the Pacific coast of northern Honshu were placed under immediate investigation for possible shake damage. That list included the Fukushima Daiichi site, the same facility that suffered triple meltdowns in the March 11th, 2011 Tohoku earthquake, and tsunami. Within hours of the mainshock, Japanese authorities confirmed that no abnormalities had been detected at any of the plants. Fukushima Daiichi was cleared last. Train service in affected prefectures was halted, including commuter lines in Tokyo, and several households experienced power outages. The system worked. The warnings fired. The nuclear inspections came back clean, and then the aftershocks started. Within the first 7 hours after the main shock, at least 14 earthquakes of magnitude 4.5 or greater struck the same segment of the Japan Trench. They clustered tightly between 39.5 and 40.3 degrees north, and between 142.8 and 143.8 degrees east. In other words, directly on top of the rupture zone. Here is the sequence as recorded in the USGS and EMSC catalogs. The main shock at 7:52 UTC, then a magnitude 5.3 at 8:03, a magnitude 5.2 at 8:08, a magnitude 4.9 at 8:14, a magnitude 5.0 at 8:23, a magnitude 4.7 at 8:30, a magnitude 5.6 at 8:32. This one unusually shallow at 2.2 kilometers depth, which we're going to come back to. A magnitude 5.1 at 9:49, a magnitude 4.8 at 10:37, a magnitude 4.7 at 10:41, a magnitude 5.0 at 10:44, a magnitude 4.5 at 11:28, a magnitude 5.1 at 12:56, and a magnitude 4.6 at 14:15. 14 events at magnitude 4.5 or greater in under 7 hours. 4 of them in the magnitude 5 range, including 1 at 5.6. Here is why that number matters. There's a statistical rule in seismology called Omori's law, which describes how the rate of aftershocks decays after a main shock. For a magnitude 7.4 event, Omori's law scaling typically predicts on the order of 10 to 15 aftershocks of magnitude 4.5 or greater spread across the first 24 to 48 hours. Read that again. 24 to 48 hours. This sequence met the upper end of that 48-hour expected count in 7 hours. And it had not decayed by the time our initial data window closed. The fault was still producing magnitude 4.5 plus events more than 6 hours after the main shock. That is what seismologists mean when they say an aftershock sequence is running hot. The sequence is outrunning the statistical model. An elevated early aftershock rate can carry several different interpretations. It can indicate a particularly stressed fault segment where adjacent asperities are already close to failure. It can indicate a main shock that did not relieve as much stored elastic strain as a typical rupture of its size should have. Or, and this is the interpretation nobody wants to say out loud, it can indicate that the main shock itself was a foreshock to a larger impending rupture. That is the scenario Japanese authorities are explicitly watching for right now. It is also the reason this story cannot be closed out at 7:52 UTC, with a green pager alert and a cleared Fukushima reactor. The magnitude, 5.6 aftershock at 8:32 UTC, is worth flagging on its own. The reported depth was 2.2 kilometers. That is not shallow in the ordinary sense of the word. That is essentially at the seafloor. Aftershocks at that depth, in a subduction zone setting, are uncommon, and when they do occur, they carry a specific geological meaning. Shallow offshore ruptures along the Japan Trench are the exact geometry associated with tsunami generation above the expected level. When a fault slips at the seafloor itself, rather than 10 or 30 kilometers beneath it, the water column above that slip responds directly. Splay faults, which branch upward from the main plate interface and surface on the ocean floor, are known to locally amplify tsunami heights. Near-trench thrust faulting does the same thing. Neither of these mechanisms is required by the 5.6 aftershock data alone, but both are on the table. This matters because the aftershock storm means the stress on this fault system is not finished redistributing itself. And when Japanese officials warned that residents should expect additional large earthquakes and the possibility of larger subsequent tsunami waves over the coming days to weeks, the magnitude 5.6 at 2.2 kilometers depth is part of why they use that language. The seafloor itself is moving, why this coast is one of the deadliest on Earth. To understand why a 7.4 earthquake on the Sanriku coast triggers this level of concern, why Japan evacuates coastal populations inside of minutes, why the nuclear inspections happen within the hour, why seismologists around the world stop what they are doing to look at the aftershock sequence. You have to understand what this coast has done to the people who live on it. 3 times in the last 130 years, this specific stretch of shoreline has hosted a catastrophic tsunami disaster. On June 15, 1896, the Meiji Sanriku earthquake generated a tsunami that reached a maximum run-up height of approximately 38.2 meters, roughly 125 feet, in the Ryori Bay area. Most shoreline measurements fell in the 10 to 25 meter range. The death toll was approximately 22,000 people. The 1896 event is what seismologists now classify as a tsunami earthquake. The moment magnitude was roughly 8.0, but the ground shaking was weak and disproportionate to the size of the tsunami that followed. That mismatch is what killed so many people. Residents did not feel strong shaking. They did not evacuate. And then the water came. On March 3rd, 1933, the Showa Sanriku earthquake, magnitude 8.4 normal faulting outer rise event on the same stretch of coast, generated a tsunami that reached approximately 29 meters at maximum run-up. 3,000 people died. That disaster struck within the living memory of survivors from 1896. Entire villages that had been rebuilt after the first catastrophe were erased in the second. On March 11, 2011, the Tohoku earthquake struck, magnitude 9.1, approximately 18 to 19,500 people dead. Some estimates, including disaster-related deaths in the subsequent weeks, push that figure above 22,000. more than 470,000 people displaced from their homes, approximately $235 billion in direct economic damage, the costliest natural disaster in recorded human history. The Fukushima Daiichi nuclear plant suffered triple meltdowns. Entire coastal towns vanished. And the aftershock sequence from that rupture produced more than 800 earthquakes of magnitude 5 or greater in the first year alone. This is the coast that ruptured yesterday morning. This is the fault family that just produced a magnitude 7.4 shallow event with 14 aftershocks in the first 7 hours, roughly 180 kilometers north-northeast of where the 2011 rupture started. When Japanese officials tell residents to stay inland until further notice, they are not being cautious. They are being historically literate. There is one specific piece of the 2011 story that every seismologist watching this event is thinking about right now. On March 9th, 2011, a magnitude 7.3 earthquake struck off the Sanriku coast of northeast Honshu, approximately 40 kilometers from what would become the epicenter of the March 11th Tohoku mainshock. At the time, the March 9th event was interpreted as a significant but standalone subduction earthquake. The tsunami was small, the damage was limited, the seismological community treated it as a completed event. 51 hours later, the magnitude 9.1 mainshock ruptured a fault patch of approximately 500 by 200 kilometers. 18,000 people died. Fukushima Daiichi melted down. The costliest natural disaster in human history unfolded over the next 6 hours. And in retrospect, the March 9th magnitude, 7.3, is now widely classified as a foreshock. The peer-reviewed literature on this is extensive. Kato and colleagues, publishing in the journal Science in 2012, documented that the March 9th foreshock was part of a slow slip event that migrated along the plate interface toward the eventual magnitude 9 rupture zone. Ando and Imanishi, publishing in Earth, Planets in Space later in 2011, confirmed the migration signature. What they found was that accelerated foreshock activity in the 48 hours before the mainshock retrospectively signaled the impending failure. In real time, nobody saw it. In hindsight, the signature was in the data. Here is why that matters for this video. As of this recording, we are roughly 29 hours out from yesterday's magnitude 7.4 rupture. If the 2011 pattern were repeating exactly, the larger mainshock would arrive at roughly the 51-hour mark, which puts that hypothetical window inside the next 24 hours. That is not a prediction. That is the timeline overlay, which is the specific reason Japanese authorities are explicitly watching this sequence hour by hour rather than treating it as a resolved event. Today's event is magnitude 7.4 to 7.5, shallow, offshore, and on the same subduction system, approximately 180 kilometers north-northeast of the 2011 mainshock. The fault segment immediately north of the 2011 rupture has been identified in multiple post-disaster seismic hazard studies, including analyses by Japan's Headquarters for Earthquake Research Promotion, as a region of elevated residual stress carrying significant unreleased slip deficit. Translation: the fault patch next door to 2011 was known to be loaded. It was known to be capable of producing a large earthquake, and it just produced one. The base rate probability that any given magnitude 7.4 subduction earthquake is a foreshock to a larger event is low, on the order of a few percent globally, but the base rate in regions with unrelieved slip deficit adjacent to a recent great earthquake is elevated. The aftershock rate running hot in the first 7 hours is not, by itself, diagnostic. What seismologists are watching for are specific signatures: accelerating moment release, migrating hypocenters along the plate interface, slow slip anomalies in GPS data, and any sign that the aftershock sequence is not decaying in line with Omori's law. A claim circulating online frames this event as the result of directed energy triggering, specifically the High Frequency Active Auroral Research Program, or HAARP, based in Gakona, Alaska. The physics rules it out. HAARP operates at approximately 3.6 megawatts of transmitted radio power and couples energy into the ionosphere at altitudes between 100 and 300 kilometers. A magnitude 7.4 earthquake releases on the order of 10 to the 15th power joules of elastic energy. The facility could transmit continuously for months without accumulating a tiny fraction of what the fault released in seconds. Shearer and colleagues, publishing in Environmental Research Letters in 2016, surveyed 77 climate and geoengineering experts and found 0 who considered HAARP-type facilities capable of triggering earthquakes. The energy budget does not exist. The mechanism does not exist. This framing is physically impossible, and it distracts from the real question on the table, which is whether this coast is done moving or Here is what the next 48 hours of this story looks like from a scientific standpoint. Japan's seismologists have the same data the rest of the world has, plus more. They have GPS strain measurements distributed across northern Honshu that can detect slow slip events on the plate interface in real time. They have ocean bottom seismometers installed directly above the rupture zone after the 2011 disaster, specifically to catch exactly this kind of event. They have decades of post-2011 research on how a foreshock sequence on this coast behaved before the main rupture. What they are watching for is a short list of diagnostic signatures. First, whether the aftershock sequence continues to run ahead of Omori's law decay. Second, whether the hypocenters are migrating along the plate interface toward an unruptured patch, the way the 2011 slow slip migration did. Third, whether GPS stations along the coast are recording anomalous motion consistent with a slow slip event that is loading an adjacent fault segment. And fourth, whether the moment release across the sequence is accelerating rather than decelerating. Japan experiences a magnitude 7 or greater earthquake on average every 16 months. A magnitude 7.6 struck Aomori Prefecture in December of 2025, only 4 months before yesterday's event. 2 magnitude 7 plus events on or near the Japan Trench in under 5 months is outside the long-run average rate. That is not the same as saying a larger event is imminent. It is saying the fault system is active, loaded, and it has been producing unusually large ruptures at unusually close intervals. The honest forecast is this. Most likely, yesterday's event is the main shock of its own sequence. The aftershocks will decay over the coming days and weeks in line with Omori's law. The tsunami warning, which was already being scaled back as this briefing was being prepared, will be fully lifted. The nuclear plants will stay clean. Japan's preparedness will have been tested and proven. That is the outcome that matches the base rates, and it is the outcome that will most likely be reported as the story of this event when the dust settles. But there is a small, non-zero probability that yesterday was the March 9th of 2011. The aftershock rate matches, the location matches, the depth matches. The adjacent slip deficit zone is exactly where the 2011 foreshock preceded the magnitude 9.1 main shock. And the 51-hour window that closed out the 2011 sequence runs out later today. Japanese authorities are telling residents to expect additional magnitude 7 class events over the coming days to weeks and to stay inland until further notice. That language is standard procedure after an event of this size. It is also not inconsistent with the higher concern interpretation. We will be tracking this closely through the rest of the week. The diagnostic signatures we listed, the aftershock decay, the hypocenter migration, the GPS anomalies, the moment release curve, will emerge in the data over the next 48 to 72 hours. If they come back normal, the story ends here. If they do not, the story is about to become the biggest seismic event of the decade. For now, the aftershocks are still coming. And the question Japan is actually asking is not whether something happened. It is whether something larger is still compressed inside that fault system and is not yet released. Thanks for watching the Space Desk. Subscribe to the channel so you don't miss any updates on this developing story. Stay safe out there. I'll see you in the next one.